Hello everyone and welcome back to memflow Applied episode 2. Yes! Oh, we overflowed and I missed the joke in the last episode. Well, let's overflow the like button then, shall we? Come on, do it. It helps the channel. Actually, it actually helps the channel tremendously. Thank you. But in this episode, we will have something very light. We will add some more types for printing variables, continuing on the quality of life ride, and we will add optional progress bars to we're scanning pointers and stuff, and well, here we are. There's the pointer, but it took this long to scan it, so I'm adding that. Let's just support any type of integer, shall we? It's gonna be really simple. So you've got i64, you've got above that i128, it will be 16, and it will be an 8. So it will be as simple as that. I8, I16, I32, I128. And let's do the same with unsigned types. So it will be RU. Right here we replace I with I. Oops, I with U. Okay, we've got that sorted. Floating points, of course. You've got F32, it will be F32, F64. We have those sorted, and we need to do the same with parse input, don't we? 16, 8, 8, 16, 128, 128, 16, 8, and unsigned versions of this are U, I to U, boom, done, and F64, F32. Is the order right? Because I'll get triggered. Yeah, we need to change the order like so. That should be it. that absolutely should be it. We need to kind of fix that U16, and it's actually UTF-16. So, oh, it needs to be format some format. Oh, it needs to be a slice of U16. We can't transmute it directly, so we need to kind of do something not the nicest thing. So we will create letmut vec equals vec. So it will be vec instead. And what this will be, we will go through the buffer window in buff dot chunks exact size of 2, and we will create a U16. How are we gonna create a U16? We're gonna create a from native endian bytes. Let s for short U16. Where the hell is that? U16 from native endian bytes, and it will be just a w.try into, and we unwrap it because there's absolutely no way it fails. So we have that, and we just push back.push the short value. Oh, it will be iter. Oh, and it's a for loop. Oh wait, it's not iter. It's like so. And I believe we've got the UTF-16 string sorted. So let's just try it out once again. What happens if, for instance, we search for I16 668? Right, we've got a few matches. 669. Now we've got 2 matches. And now let's write just the first one. Write 0, the index 0, once minus 15. And we've got the minus 15. And now this becomes 65,000 because the tick is unsigned. But it all works really nicely. We print and we've got minus 10. And what's gonna happen? We got minus 5, -4, -3, -2, -1, right? -1, what happens afterwards? 0. Okay, so if we only have access to the lower part, this is 65,000, but it sees 2. Let's reset and let's scan for str utf-16 structs bin. We've got that. What if we write to everyone once tracts bin? Doesn't change. Doesn't change. Okay. I thought maybe this would change, but no. Alas, no. Now it failed to find the process. Oh, it failed to find the process because we overrode the name, of course. What do we have here? What do we have here? So we have... Actually, we don't have these target strings anymore. Let's add the progress bars, right? And that will be a crate called PBR, and it's 1.0, but we will do it optionally, so will be version equals 0.0, optional equals true. Features, default equals progress bar, and progress bar uses, well, it uses PBR. So now, once we have that, we are gonna just add that in. pbar.rs. Let's create a really simple progress bar structure. Public module pbar. Apparently we can have it empty, which is really good because what we can do right here is use config feature equals progress. I think, yeah, progress bar. And then we just gonna use a pbar as in pbr progress bar. As simple as that. And now we implement pbar. We implement, well, we'll implement pubfn new, and that will be max length u64. This is what it uses, u64. Return self, and it uses self, and the same thing. pbar will be pbr progress bar new max length. But what we need to do is we need to use this config feature. It's disabled, yes. Why is it disabled? It should be enabled by default, which is interesting. It doesn't because it's like so. And now we're back at it again. And what do we miss? A type argument missing. And we need to use std out. std io std out. Here we go. Now that's here what we need. And now we implement. We use the same config feature. Implement pbar. So essentially this progress bar, it accepts a max length, as in the value it reaches to reach 100%. And we have the add value, which will be add u64. It will add to mutable self, essentially self.pbar.add a value. And that's all that it adds. So it adds to it, and that extends the progress bar. Essentially, that's what it is. And we have the final thing. It will be pubfn finish itself, which will be self.pbar.finish. And those are the two functions. And what we're gonna do, well, implement the same functions or not progress bar. They will be just empty implementations. Here we go. That's the thing. The not needs to be right here. And that's it. So this is inactive, this is active, and we just use the progress bar, shall we? Up scanflow src, let's add it to, for instance, this assembly module, right? Use crate pbar. All right, this needs to be a public struct. So we use that, and we create a pbar. pb equals pbar new And it will be, well, the modules, we just sum the module sizes. Modules.iter.map, and it will be module.size, I believe, as U64, sum it as U64. That's it. And what we're gonna do right here, we're gonna add bb.finish right here. They just do module by module, as simple as that. It will be m.size. Yeah, m.size. Oops, I closed it. But that should be enough. Yeah, here we go. So we have the print for the sizes. It shows the bytes right here, which is, you could say, a bit concerning that it prints the bytes like so. Can we change this to like print sizes and stuff as bytes? Bytes view as bytes, right? Let me red equals this. And this is kind of ugly, but this is the kind of thing why we put it into a separate module. If we don't, then you will end up with lots of these config checks inside the code. So it will be not good. So it will be red.pbar.setUnits, and it will be pbr units bytes, and we return the red thing. Right, as simple as that. And we just drop the disasm right here, and we just do true as the bytes. Here we go, it shows megabytes. It's awesome. It shows how much it's disassembling and how much it has disassembled. But I think that's really awesome. Now we do the same thing with, for instance, pointer map. So with pointer map, we just do, it's gonna be roughly the same thing, but not quite. So we create the PB, which will actually iterate mem map, and it will take the size of the mem map. We do that, it's cool. I think we have to do it like so. And we need to import, use create pbar. And once you have that, we're gonna go ahead and, I mean, we can add it every page. Yeah, I think that's doable. We just go ahead and do pb.add Xerox 100, which is one page. And we do the inverse map thing. It's not gonna take that long, I believe. I would just do pb.finish. And we're just gonna do pm. And it has the whole thing. It prints it, but we don't need to print this anymore. There you go. This looks really good in my opinion. It just goes and scans really well. And you have the progress, the sense of progress. It's stuff is happening. So yeah, we do the same thing for our value scanner. So we create the pbar. We use pbar, a simple pb.add Xerox 100, and pb.finish. And this here, it has cell.memmap. And we don't print this anymore. And now, well, now we shall search for something like 96. I64 96. And we search through it, we've got the matches and stuff. It's really cool. Another progress bar right here, which will be very, very different. Instead, it will be all the matches dot length as U64, and it's no longer bytes. And what we're gonna do, pb.finish, and we're gonna do a simple pb.inc, for which we're gonna add a pb.inc function, cell.pbar.inc, right? And right here. And we have that, and we have that, and we're gonna have I64 96. We search for 96, and well, it's near instant. You can see it's just does it 16 matches. And now, finally, do we have anything left? Value scanner, disassembler, those don't have anything but the pointer map. We have this, the find matches, and this is a tougher one, I'd say. Purely because it just has these recursion levels, and I wonder how to best handle it. So how do we handle walk down range? That's the trickiest part. Well, you can't calculate the whole thing, the whole, range, because it's just impossible. It is quite impossible. What you can do, create a progress bar for the range and do it on the first level, increase the progress bar. That something like that could work. I hope so. Yeah, let's just try that. Let's create a progress bar. So we're gonna do let p bar pb equals p bar new, and we're gonna do max length. It's going to be range.0 plus range.1, the whole range, and we need to do this as u64. And we're gonna do pb.finish right here, pb.set0, something like that, and we go to p bar value u64. We don't care about you, but right here we do and set value u64, and we just do self.set value. Oops, self.pbar set value. Here we go. That works. And we just do pointer map. We pass the PB. We will have the PB right here. PB P bar. So what we can do one more thing, and that is changing the search for signature. Search for.len. And instead of setting this right here, we just pass in address. So this way, we actually know the length, of the addresses. And this is gonna make it, oh, this is not ideal. Why does it mess up with M? Come on. Come on. Here we go. Oh, M right here. Here we go. Now we just need to fix this. So this will be actually better because we don't just copy the values like that. Okay, future Ori here. I'll show you real quick how to fix this whole progress bar, make it absolutely perfect. So first of all, instead of calculating the range, we just pass a percentage value of 100,000. So it would be 100 and then the point values. So you have this progress bar with 100,000 max value. Then what we're gonna do, create a part, how much one single element uses of the whole progress bar. So it will be let part equals 1.0 divided by search for dot length as f32, and this will be percentage. It's very important. Right now in the progress bar we will do create an iterated enumerated iterator. And once you have that, we will pass through to the walk down range function, a subpart of the progress bar. And you will see in just a second how awesome that is. So we have part multiplied by I as f32, and then the ending part. So we will have just a tuple of start and end, indicating the range of the progress bar. So we will have part times I as f32. I start at 0, so it will be from 0 to +1 as f32. And once you have that, right here in the progress bar, we're gonna have set 100,000, but 0 multiplied by part times I plus 1 as f32. And what this will do, we will just wrap it into dot round as U64. This will give us the value after this walk down range finishes. But now in the walk down range function, what we're gonna do, we're gonna pass pb start and pb end. It will be f32, f32, and once you have that, we go into this particular function where we recurse inwards, and we're gonna add the magic which gonna make a really smooth progress bar. Rather smooth, without compromising performance. So instead of these level checks, we don't do them anymore, and we don't do this here. Instead, we have this subfraction right here, pb start and pb end. So once we iterate through them, we're gonna create another subfraction within that that's gonna lock the progress bar in. So it's gonna be, well, calculate a new starting position. So it will be fraction start. It will be last minus minimum as f32 divided by max minus minimum as f32. If you think about it, this is gonna ignore, essentially the starting fraction is gonna ignore everything that was before last, and we create new start, which will be a scale fraction. It will be pb start plus pb end minus pb start, which is the range, multiplied by frac start. And that will give us a new starting position, which we will be able to pass through. And we need to do the same thing with the ending position. And we want it to be accurate, so we won't do floating point addition, and instead we're gonna calculate it using frac end equals k minus min as f32 divided by max minus min as f32, and then we'd be new end equals, well, it's gonna be pb start plus pb end minus pb start times frac end. Once you have that, we just need to assign last as usual. We're gonna do the same thing right here with the fraction thing. It will be calculate how much space each subitem uses in the fraction. So it will be let part, the same way as in the other function, equals new end minus new start, and we divide that by vec.length as f32. And right here, the same thing, we have I and v, hr dot enumerate, and we're gonna have a, well, new start plus part times I as f32, new start plus part times I plus 1 as f32. And that is it, I believe. Oh wait, we're missing one final thing, and that is, of course, setting the actual progress bar intermediately. And we don't want to call the progress bar function all the time. We're just gonna ignore if the values are very, very small. So if new end minus pb start is more or equal to 0.001, for instance, or just add another 0 for good measure, we're gonna do, well, we're gonna do pb.set, and it will be new end times this scaled very, very perfectly as f64. Oh, as u64. And you have this, and let's run it, shall we? We have our scanner, and we will search for strasfd, which is a string, the name I passed through, and it will be offset scan, yes, 200, 206, for instance. And that was instant. Offset scan, yes, 200, 207. As you can see, this is much like it's jagged, but it's much smoother at the same time. There are way more updates happening. So yeah, this is a new implementation which we're gonna have in our code. Print the matches, and we just change this right here to max print to actually print like 16 matches. So it's not too big, it's not too small, whatever, it's okay. Well, 32, let's say 32. But yeah, this was it. This was the episode. It was not very much to it, but I had exams happening, so it was tough to juggle things around. But next episode is gonna be really awesome. Next episode, I teased it last time. I'm gonna add pattern making, pattern sig maker thing that you have on IDA. We're gonna do that here for like our whole pattern scanning thing, and it's gonna be awesome. I'm not exactly sure how I'm gonna do it, but I think I'm gonna do it. So here we go. Thank you very much for watching. All right, you absolutely know the drill. Overflow that like button, hit subscribe for more content like this. It's gonna help me absolutely tremendously. Next episode, I'll get something really pristine quality out, and we're getting close to having a full blown tool to do stuff, and I'm very happy for it. So yeah, in this episode, what we did, we added those progress bars right here, for disassembler, for pointer map searching, for pointer map making, for value scanner. It's like makes things visual. Yeah, this stuff is happening, and I think that improves quality of life quite significantly. We enabled scans of all different types right here, you can see, and they're absolutely awesome. We just can't scan for anything, even floats. It's cool, and I think that's roughly it. uh so next episode, awesome. See you there. Don't forget, my name was Heap, yours was undefined. See ya.